Okay, 3.2 characteristics of polynomial functions. So we're going to talk about end behaviors of polynomials. Okay, end behavior describes the values of the function f at x as x takes on large positive or large negative values. Okay, so what that means is that we're going to be looking at a graph on a Cartesian plane with x and y, and we want to know what is y doing. Okay, so we always look at the y's, oops, and we quote it. So we reference in the domain, or in, you want to call it in like an interval, or in the x's. Okay, but we're looking at what's going on with the y's. So we want to know as x approaches a really, really small number, which is like negative infinity, right? Is the y going up to infinity or down to infinity? Or even approaching an asymptote, okay? And then we're going to talk about as x approaches positive infinity, which is going to be a really, really, really large positive number, what's y doing? Is it approaching infinity, negative infinity, or are we like approaching an asymptote? Okay, so we're going to get into this and graphing. So for large values of x, the graph of the polynomial function, okay, and then we have just the general form here of a polynomial function, resembles the graph of the power function. This means end behavior is determined by two things. Okay, we're going to decide what is the degree of the polynomial. Okay, is it even or odd? And then what's the leading coefficient? Is it positive or negative? Okay, so degree and leading coefficient. I'm going to short form degree with a D and leading coefficient with an LC. So there are 4 different scenarios. So if we have an even degree, which is always what we check first, one of two things is going to happen. Either we're going to have a positive leading coefficient or a negative leading coefficient. Positive leading coefficient, the end behaviors are both going to approach infinity. Okay, so as x approaches negative infinity, y approaches infinity. We can interpret this as our x and y axis. So as x approaches negative, y approaches positive. Then as x approaches positive, y also approaches positive. Okay? And if you want to do it in quadrants, we're going from quadrant 2 and it tails off in quadrant 1. Now, if we have a negative leading coefficient, what's going to happen, I'm going to put this underneath, because I think of this kind of as a parabola. When I am doing even degree, I think parabola, right? So parabola opening up, parabola opening down, and I think of the leading coefficient as the a value. So as x approaches negative infinity, y approaches negative infinity. As x approaches infinity, y approaches negative infinity as well. So this would go from Q3 to Q4. Okay, now if the degree is odd, there are 2 different things that can happen. Okay, so if the leading coefficient is positive, and remember, we're thinking for an odd function, think line. So we're either going to go up to the right or down to the right. And then we're thinking like positive slope or negative slope. So positive slope, think of a line, but this is going to be a curve. So as x approaches negative infinity, y approaches negative infinity. Okay, we're going to go from quadrant 3 to, as x approaches positive infinity, y approaches positive infinity, so Q1. Just like a line would. Right, just making those connections. Okay, and what about negative? If we had a negative slope, our line would look like this, right? So the same happens if we had x cubed, x to the 5, any odd degree. So as x approaches negative infinity, y approaches infinity. As x approaches infinity, y approaches negative infinity. And we can say that this is Q2 to Q4. Okay, let's talk about turning points and zeros. So the number of turning points. A turning point is where a graph changes from increasing to decreasing or vice versa. A polynomial has at most n minus 1 turning points. This is very general. It gets a little bit more complicated, but at most. So if we have like degree 3, you're going to have at most 2 turning points. I'm just going to put TP. And each turning point is a local max or a local min. So the example of this would be if we had 1, 2, 3. So we have 2 turning points there. Okay, and then number of zeros. We'll do the same example. A zero, also called a root, is where a function equals 0. This is the x-intercept. So take a look at this one. If this is an x cubed graph, we say that there are 3 x-intercepts. So a polynomial has n real zeros. And then again, that's at most. I'm going to change this here. A polynomial has at most n real zeros. So for each of the following functions, describe the end behavior, the possible number of turning points, and the possible number of zeros. So when it says possible, we're thinking like the maximum. At most, okay? So at most for these two. And then use the information to sketch possible graphs of the polynomial. Okay, so without actually factoring this, figuring out the zeros, everything, we're just going to sketch. So for the end behavior, we need 2 things. We need to say, what's the degree of this polynomial? Well, taking a look at the exponents, 5, 3, 2, and 1, I have this as degree 5. Therefore, it's odd. So in the chart above, it's odd. Okay, so now we're down to 2 different outcomes instead of 4. Now the leading coefficient is on the degree 5, so the leading coefficient is -3. That means that it's negative. Okay, if we are an odd degree, we're thinking, inside of the paper, we're thinking a line, and we're thinking negative slope. So we're thinking from here to here. This is my thought process. So I'm going to do end behavior as x approaches negative infinity, and as x approaches infinity, y approaches infinity, and then y approaches negative infinity. Okay, possible number of turning points, it's going to be n minus 1. So turning points, I'm just going to short form it TP, n minus 1, which is 5 minus 1, which is 4. So maximum number of turning points is 4. Now possible number of zeros, n equals 4. So since it's degree 5 and it starts in quadrant 2, we're going to zigzag 5 times. 1, 2, 3, 4, 5. And this is automatically going to give us 1, 2, 3, 4 turning points. So that works. Oops, I put 4 for this. This is 5. Okay, and it's automatically going to give us 1, 2, 3, 4, 5 x-intercepts. Okay, B. So we first want to determine the end behavior. So we need two things. We need the degree, which we have 4 and 2. So the degree is 4. It's always the greatest exponent. And we need the leading coefficient, which is on the term with the greatest exponent. So that's 2. So we're looking in the chart above for degree 4, which is even, and leading coefficient, which is 2, which is positive. So again, think quadratic. Okay, if we have a quadratic that has a positive a value, we're thinking opening up, right? So this is going to be as x approaches negative infinity and as x approaches positive infinity in that order, because we read from left to right. Okay, it's just like we would put here. As x approaches negative infinity, y approaches infinity. As x approaches positive infinity, y approaches infinity. Okay, number 2, maximum number of turning points is going to be n minus 1, which is 4 minus 1, so it's just 3. And then the roots, maximum number of roots is going to be n equals 4. So now let's go ahead and graph this. So because we have an exponent 4, I'm going to zigzag 4 times. So 1, 2, 3, 4. And then we can do our checks. Okay, so turning points, 3, 1, 2, 3, that works. Okay, and then roots 4, 1, 2, 3, 4, that also works. Example 2, what could the graph of a polynomial function that has a range of this and 3 turning points look like? Okay, so if I were to draw an x and a y axis, I know that the range is from negative infinity till 10, okay? So this is not a vertical asymptote. This is just me saying, okay, this is like the maximum that it's gonna reach. So here's the thing. We know that if we're staying below 10, we're going to have to start in quadrant 3 and end in quadrant 4 if we're looking at a polynomial. Okay, so this is going to have to be an even degree. So it's either going to have to be x squared, x to the 4, x to the 6, so on. Okay, that's what we have the information for so far. Now, it's going to have 3 turning points. So when we take a look at turning points, we know that the turning points, the maximum is n minus 1. So if it has 3, so the turning points are 3, I'm going to bring over that negative 1, and I'm going to say the number of turning, the degree is going to be 4. Okay, so we're able to draw these they're not end points, they're like end arrows. And then let's draw degree 4, so zigzag 4 times and touch this 10. So 1, 2, 3, 4. Okay, so this satisfies that the range is negative infinity all the way up to 10. And there are 3 turning points, which are here, here, and here. I do want to point this out. So in this scenario, there are only 2 x-intercepts. If this question had a requirement for x-intercepts, we may have had to like go down more with this. And then that turning point would be here still, and it would still satisfy. Another way, so that'd be like 4 x-intercepts. And another way is if this hit right there, it'd be have